Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about example of autocorrelation function and covariance function. The example is if a random process x of t is sine of omega t plus y, where y is a random variable uniformly distributed in the interval 0, 2 pi. So prove that covariance of t1, t2 is equal autocorrelation of t1, t2 is equal cos omega t1 minus omega t2 by 2. Coming to the solution, given that the random process x of t is sine of omega t plus y, now here omega is a constant and y is a uniform random variable over the interval 0, 2 pi. So over this interval, the uniform probability density function of the random variable y is f of y or fy of y is equal 1 by 2 pi over 0 to 2 pi. First calculate the autocorrelation function of the random process x of t. So we know that the autocorrelation function of x of t is rxx of t1 comma t2 is equal expectation of x of t1 into x of t2. So given that the random process x of t is sine of omega t plus y, so x of t1 is sine of omega t1 plus y and x of t2 is sine of omega t2 plus y. So now here this within the bracket term is 2 sin A sin B expansion and the 2 is missing. So multiplying numerator and denominator by 2 we get Rxx of t1 comma t2 is equal. So expectation of this within the bracket term is cos of A minus B minus cos of A plus B, and this is the A term and this is the B term. So cos of omega t1 plus y minus multiplying minus this B term minus omega 2 minus y minus cos of A plus B, cos of omega t1 plus y plus omega t2 plus y by 2. So 1 by 2 is constant, that is written before expectation. Now here the first term plus y and minus y is the cancel and the remaining first term is expectation of cos of omega t1 minus omega t2 minus cos of omega t1 plus omega t2 plus 2y. Now applying the expectation into each term, Rxx of t1 comma t2 is equal 1 by 2 into expectation of cos of omega t1 minus omega t2 minus expectation of cos of omega t1 plus omega t2 plus 2y. So using expectation of x of t expression, so in this case function is cos of omega t1 minus omega t2. In this term the function is cos of omega t1 plus omega t2 plus 2y. So 1 by 2 by 1 by 2 integral 0 to 2 pi cos of omega t1 minus omega t2 into, now here the y is the random variable and its probability density function is 1 by 2 pi into dy minus 1 by 2 integral 0 to 2 pi. Here the function is cos of omega t1 plus omega t2 plus 2y into density function of the random variable y is 1 by 2 pi into dy. So 1 by 2 pi is constant, that is before integration. Now here in the first term integrating with respect to y, cos of omega t1 minus omega t2 is also constant, that is written before integration. And integral 1 dy is y over 0 to 2 pi, and after substituting upper value of theta and lower value upper value of y and lower value of y, we get 2 pi minus 0 is 2 pi. So 1 by 2 pi into 2 pi is the cancel. The first term is 1 by 2 cos of omega t1 minus omega t2 minus 1 by 2 into 1 by 2 pi. Integral of cos is sine of omega t1 plus omega t2 plus 2y. Now we are integrating with respect to y, so divided by 2 over 0 to 2 pi. In this second term, substitute upper value of y and lower value of y. Substitute upper value of y and lower value of y. Now the first term is here sine of 4 pi omega t1 plus omega t2. Sine of 4 pi plus omega t1 plus omega t2 is sine of omega t1 plus omega t2, and substitute upper value of y, and the second term is minus sine of omega t1 plus omega t2, and the plus term and minus term is cancelled. So within the bracket term is 0. 1 by 4 pi into 0 is 0. So therefore the second term is 0. Therefore the final value is Rxx of t1 comma t2 is equal 1 by 2 cos of omega t1 minus omega t2. So this is the value of autocorrelation function of the random process x of t. So next calculate the covariance function of autocovariance function of x of t. So we know that covariance of t1 comma t2 is equal expectation of x of t1 x of t2 minus expectation of x of t1 into expectation of x of t2. So this first term is the autocorrelation function of the random process. This value is already calculated and it is 1 by 2 into cos of omega t1 minus omega t2, and separately calculate expectation of x of t1 and expectation of x of t2 value and substitute that values into this equation. Finally we get covariance of t1 comma t2. So now first calculate expectation of x of t1. So the expression of expectation of x of t1 is integral minus infinity to infinity x of t1 into density function into dx. So given that x of t is sine of omega t plus y, now your x of t1 is sine of omega t1 plus y into fy of y dy. So given that the density function of the random variable y over the interval 0 to 2 pi is 1 by 2 pi, and so that is expectation of x of t1 is equal integral 0 to 2 pi sine of omega t1 plus y into 1 by 2 pi into d pi 1 by 2 pi into dy. Integral of sine is minus cos integral of sine is minus cos of omega t1 plus y over 0 to 2 pi. Now substitute upper value of y and lower value of y. We have minus 1 by 2 pi cos of omega t1 plus 2 pi minus cos of omega t1 plus 0. Cos of 2 pi plus omega t1 cos of omega t1 minus cos omega t1 plus cos omega t1 minus cos omega t1 is the cancel. Therefore expectation of x of t1 is equal to 0. So similarly calculate expectation of x of t2. So the expression of expectation of x of t2 is integral minus infinity to infinity x of t2 into density function into dx. So now substitute x of t2 value, given that x of t is sine of omega t plus y, x of t2 is sine of omega t2 plus y. Now where the y is the random variable density function of the y into dy. Now applying the given data, expectation of x of t2 is equal integral 0 to 2 pi sine of omega t2 plus y into 1 by 2 pi dy. So integral sine is minus cos of omega t2 plus y over 0 to 2 pi. Now substitute upper value of y and lower value of y. We have minus 1 by 2 pi cos of omega t2 plus 2 pi minus cos of omega t2 plus 0. Cos of 2 pi plus omega t2 is cos of omega t2 minus cos omega t2 is the cancel. The RHS term is 0. Therefore, expectation of x of t2 is equal to 0. Substitute expectation of x of t1 and expectation of x of t2 and expectation of x of t1 x of t2 values into the expression of the covariance of t1 comma t2. So therefore covariance of t1 comma t2 is expectation of x of t1 x of t2 values 1 by 2 cos of omega t1 minus omega t2 minus expectation of x of t1 value is 0 and expectation of x of t2 value is 0, 0 into 0, 0. So therefore covariance of t1 comma t2 is equal to 1 by 2 cos of omega t1 minus omega t2. So now here the given random process x of t is sine of omega t plus y. The autocorrelation function of the random process x of t and autocovariance function of the random process x of t both are same.